Hello everyone, and welcome to today's webinar. STL file editing is finally easy with Fusion 360's new Parametric Mesh Workspace. My name is Maria Ma, the Marketing Campaign Coordinator for Engineering.com, and I'm happy to welcome our speaker for today, Jason Lichtman, Senior Technical Specialist for Design and Manufacturing at Autodesk. Jason is a seasoned product design engineer professional who has 15 years of experience taking ideas and turning them into industry-leading mass production products for well-known brands. Now, before we get started, just want to cover a few housekeeping items. Today's webinar will be recorded, then available for on-demand replay on engineering.com. For attending our full live session, you'll receive your PDH certificate within 48 hours. And if you have any questions, please submit directly in your webinar interface, and we'll try to address all questions during Q&A. Now I'd like to kick it off with a couple of poll questions. Please let us know, how many years of experience do you have working with mesh files? Less than a year, 1 to 2 years, 2 to 5, 5 to 10, or 10 plus years? We'll give you a moment to respond. So we have at 31%, less than a year. 23% is tied with 2 to 5 years and 10 plus years, and 19% selected 5 to 10 years. Thanks so much for that. And we're going to launch another one. We'd also like to know, what is your current or primary CAD software? Fusion 360, SolidWorks, Creo, CATIA, NX, or Onshape, Mesh Editors, or other? We'll give you a moment to respond. So majority selected SolidWorks, so that's 41%. 21% selected Creo, CATIA, NX, or Onshape. And tied at 17%, we have Fusion 360 or other. Thanks so much for everyone who participated. And now without further ado, I'll pass it over to our presenter. Jason, over to you.
Excellent. Thank you so much, Maria. It is my pleasure to be with all of you today on engineering.com. Today we are going to be talking a lot about STL files. So the question of the day is really, why are we focusing on mesh files at all? This post from Facebook, I think, tells it all. Hi guys, I'm new to 3D printing and the CAD scene. Love all the content. Some of you guys are seriously talented. Thank you. Quick question, can STL files from Thingiverse be reverse engineered? Can I take an STL file, re-upload it to Tinkercad or Fusion 360 and modify them? These are the kinds of questions that we see all the time. But more important than the question is the answer you're going to see very commonly. Things like, good luck with that. You might as well just remodel that part from scratch. Or forget the STL, just convert it to a solid and then work with that. You'll get a wide range of answers, whether those people asking the questions are new to CAD or new to 3D printing or experienced veterans. You will see these same questions over and over and over again. And the key here really is an understanding of what STL files are, why they're problematic or have been problematic in the past, and how Fusion 360 can help make STL editing significantly easier than you've ever experienced before. So today's topic, we're going to talk all about STL files, all the way from the foundation principles to what you can actually do with them today with new capabilities. And all of this is really possible because Fusion 360 released a huge update. We call it a major update, and that was on July 6th of 2021. And that included an overhaul of the mesh workspace and the mesh capabilities. So what you used to be able to do in Fusion 360 was already powerful, but what you could do today is incredible. Far superior than anything I've seen in any of the other CAD applications that are out there. And so it's my pleasure to show you how that's going to work. But before we do that, we have to cover a little bit more of the basics. Let's actually go over what our agenda is in particular. I'm going to tell you a little bit more about me. I'm going to then tell you a little bit about Autodesk, because a lot of you out there, the majority of you actually, are not Autodesk or Fusion 360 users. So we want you to understand a little bit about us as a company and why we're trying to solve this problem. Then we're going to talk all about mesh files, that foundation that I was talking about earlier. We're going to tell you all about why working with mesh files is difficult, and it's really all about how they're defined and how the CAD applications that you're used to using choose to define their geometry. So we'll cover those basics, and then we're going to get into the really good stuff. What can you actually do with STL files today in Fusion 360, and how does that compare to what you may or may not be able to do in your current application? So with that, let's talk a little bit about your speaker. That's me right there. I'm Jason Lichtman, and as Maria mentioned before, I'm a senior technical specialist for design and manufacturing here at Autodesk. I focus specifically on Fusion 360. I come from industry. I spent 10 years in particular as a product design engineer, a professional product design engineer that is, taking ideas, turning them into 3D models, turning those models into prototypes, and those prototypes into mass production. But really, I've been in the entire industry for well over 15 years, taking those ideas and turning them into real products. My specialties include things like 3D printing, 3D scanning, reverse engineering, and design of molded parts for injection molding, for composite molding, and a variety of other molding processes as well. But I think I'm going to be a great fit for today's topic. Now let's talk a little bit about Autodesk. You probably have heard of Autodesk before, but more often than not, you probably are thinking of AutoCAD. Autodesk is the AutoCAD company, but it's actually a whole lot more. Founded in 1982 by John Walker, Autodesk has created a variety of different CAD applications to serve a variety of different industries. In particular, we segment ourselves into 3 industries: architecture, engineering, and construction. Think about building buildings or designing infrastructure like tunnels and bridges and a whole lot more. Autodesk has a variety of different tools at your disposal for those particular applications. Some of the products you may or may not have heard of include AutoCAD itself, including the specialty versions of AutoCAD, Revit, Civil 3D, InfraWorks, Navisworks Manage, Advanced Steel, Robot Structural Analysis, and a whole lot more. We also are very big in what we call the media and entertainment industry. So think about animation and effects, virtual reality, augmented reality, and a whole lot more. Our softwares in that field include Maya, 3ds Max, Arnold on the rendering side of things, Motion Builder, and Mudbox, a fantastic STL editor, by the way. We also have an entire segment or division of our company that's focused on product design and manufacturing. And that is what we call the design and manufacturing side of our business. And we include CAD or computer-aided design, CAE or computer-aided engineering, those are the analysis tools, and CAM or computer-aided manufacturing to help take those ideas and turn them into real products. We have a variety of different softwares that help you in this space, including Autodesk Inventor, AutoCAD, Fusion 360, Navisworks Manage, Vault, and a whole lot more. But our emphasis today, or focus today, is going to be on Fusion 360 in particular. And if you haven't used it, this is what it looks like, or at least what the user interface looks like. Fusion 360 is a CAD, CAE, and CAM tool. It's a platform, actually. And a platform, in this case, means that it really is trying to take all of the different aspects of your design, analysis, and manufacturing and put it under one roof, so to speak. So if you're an industrial designer, you can be using Fusion 360. If you're a mechanical engineer like me, also, of course, using Fusion 360. But if you're designing electronics, maybe you're an electronics engineer, you can use the same exact CAD solution to design the PCB as you would design the enclosure around it. That in itself is a pretty powerful thing. Not only that, you can analyze the parts for structural stability, for thermal transfer, for fluid flow, and a whole lot more, all in one platform. And when you have that part already ready to manufacture, you can actually program those toolpaths and then actually manufacture it from Fusion 360 itself. So when we're talking about what Fusion 360 can do, it can do a whole lot of different things. But it's not just about any one of those things, it's about being able to do all of them under one roof, under one platform. And that's what Fusion 360 is all about. So now that you understand a little bit about Autodesk and about Fusion 360 as a CAD platform. Now let's talk a little bit about meshes, right? That's what you came here for. So again, we're going to talk a little bit about what a mesh body actually is, what a BREP body is, and if you've never heard that term, you are going to learn all about it. We're going to talk about the differences between the mesh bodies and the BREP bodies, and therefore we're going to explain why mesh files are so hard to work with and or edit, or at least they have been traditionally. So let's jump into the good stuff. We have to start with some basic definitions. So a mesh body is a body or object that is made of polygons, typically triangles. So on the left, you could see that it's a triangle-based polygon or polygonal model, as sometimes we call it. And on the right, you're seeing another body. This is also a mesh body. This one happens to be made of polygons that are squares or quads. Both are mesh files, and you'll see a lot of common formats like STL, OBJ, 3MF, and FBX. Are there differences between these file formats? Absolutely, but they are all mesh file formats. If you ask me personally which one I prefer, 3MF, and you'll see why in just a few minutes. Now let's talk about that BREP body that we talked about earlier. BREP is short for boundary representation or boundary representational surface or solid, right? So it's the way that you define the object. So if we go back a slide here, this object is defined by the polygons. So it's a bunch of points in space that are connected with these triangles or with these quads. And the alternative is to define this body based on the boundaries. And that's why they call this boundary representation or boundary representational surfaces and solids. So this is just a different way to define the actual shape. And you'll see a lot of common formats. So IGES files, step files, SAT files, parasolid files, which go by X_T or X_B, IPT, which is an inventor file format, CATPART, which is a CATIA file format, SLDPRT, which is from SolidWorks. 41% of you apparently are coming from SolidWorks, so you recognize that one very well. But there's a whole lot of different file formats that are all BREP. And the reason that they are BREP bodies is because the way that the programs are defining those shapes based on the way that the program itself works is by the boundary itself, right? Now, to understand this a little bit better, we're actually going to go a step back. We're going to talk a little bit about 2D images, and I promise you this will be worth it. If you haven't heard this analogy before, and you probably haven't unless you've seen another one of my webinars, I think you will enjoy this. So let's talk about ways you could represent a 2D image. On the left and on the right, you can see Autodesk logos. And by the way, for any of you that don't recognize this particular logo, Autodesk just rebranded itself. So this is a brand new logo. And you can see the same logo on the left and on the right, and they look exactly the same on first glance, except for the fact that the one on the left has above it vector, and the one on the right says raster or bitmap above it. Now, one of them is defined mathematically, and one of them is defined based on pixels. But again, on first glance, they appear to be exactly the same. It's when you start to look at them under the hood in a little bit more detail that you'll start to see some differences. And hopefully the resolution on your end is coming out clear enough that you could see that the one on the right is actually a little bit blurry. And if you're not seeing that now, let's zoom in a little further. Now, I very much hope you see this. The one on the right, the raster or bitmap image, is coming out blurry because it's defined based on those pixels. Pixels are little tiny squares or little dots that represent a color. And the colors you could see here are, when you zoom in, are going to end up looking a little bit blurry. Now, if you zoom in even further, you can see even now there's a grid, and that just helps you define so you could actually see that. Now, there are different softwares to be able to create the vector files versus being able to create the raster or bitmap images. I'm going to focus on one example. This is from Adobe. Adobe makes a software called Adobe Illustrator, which is a vector-based image editing program. And they also make Adobe Photoshop, which is a raster or bitmap image editing program. Both of them, you can open that logo just fine. And so you can see the logo on the left and the right in both of these softwares. If you start to zoom in, you're going to start to see those differences again. But I also want to point out that the one on the left has a blue box around it. It's treating the A as an object, whereas the one on the right is really just a collection of those pixels. I'll also point out that the tools you have in the softwares themselves are totally different, because the one on the left is based on the vectors. So the operations or what you do with it are a lot more like Boolean combine, like cut the thing in the front or keep the thing in the front or unite them together. Whereas the tools in Photoshop, the raster or bitmap image editing tool, are much more like brushes. You're editing on a pixel by pixel level, whatever it is on the screen. All right, so you have very different tools based on these two different softwares, even though they're really opening the same thing, right? The Autodesk logo. Now, in terms of compatibility, this is where it starts to get really interesting. You can take a vector from Illustrator and you can actually open it in Photoshop. And when you have it in Photoshop, you're going to find that there's limited use in what you could actually use it for without converting it, which we'll talk about in a moment. You can also take the raster or bitmap image from Photoshop, and you can actually open it in Illustrator, right? The vector program could still open that bitmap or raster image. But when you do that, you will again find limited use in what you can actually do with it without converting it, because the tools that are in Illustrator are again meant for vectors, not really meant for the rasters or bitmaps. And that makes sense once you think about it this way. Now, what if you want to actually convert it? I mentioned we'll talk about that. So if you have a vector and you want to convert it into a raster, we call this rasterizing, and you can rasterize or raster a vector no problem. When you do, it's going to look like the one on the right, and this one you could see, I left the little pixels in there so you could see it a little more clearly, but in reality, this is very high fidelity, and this is going to come in really nice and clear when you take that vector and you rasterize it. Right, so the one on the right now shows you what it would look like nice and crisp and clear. The other way around is the problem. So if you start with a raster or a bitmap image and you want to convert it into a vector, we call that vectorizing, sometimes called image tracing. But if you want to do that, it is low fidelity. It does not really come in that clear. Now, at first glance, you might look at these and say, I don't know what Jason's talking about. Those look fantastic. But when you zoom in, you're going to see that there are some details here that are a little bit wrong. So when you're vectorizing, there are aspects of that image that are converted into a mathematical formula, and it just doesn't do it perfectly. So you end up with a lot of little things you might need to clean up later. Now, how do we take that 2D image analogy and apply it to 3D? Right, I already defined for you that the mesh file is really just a way to define something in 3D, and the boundary representation is the same, it's just a different way to define it in 3D. Well, now let's talk about that in comparison to the 2D analogy, right? So these are different ways you could represent things in 3D. Remember, I told you that the engineering softwares like Fusion 360, SolidWorks, Creo, NX, CATIA, they all use this boundary representation to create the solids and surfaces. There are, however, a lot of other ways you can represent geometry, like wireframe, point clouds, the mesh files we've been talking about, and even subdivisional surfaces. But I want you to think of them like this. I want you to think of the boundary representational surfaces or solids like a 3D vector, and I want you to think of the mesh files like a 3D raster or a 3D bitmap. And I want you to think of each of the triangles or the quads as a 3D pixel. And once you start to think of it that way, then this all starts to make sense. If you want to go from the BREP to a mesh, that's the high fidelity, really easy, quick conversion. And you probably design as a BREP, and last second before you go and send something to your 3D printer, you convert it to a mesh and you 3D print it, no problem. But it's the other way around that's problematic. You want to take a mesh file and turn it into that BREP solid. That's a low fidelity conversion. And in a lot of cases, you can't even do that. A lot of softwares out there will not let you import a mesh at all. And if they do let you import a mesh, you're very limited in what you could do with it. And it's basically just there as an underlay for you to design something from scratch on top of, right? Like image trace, so to speak. And that's why when you saw that Facebook post about someone saying, can I just take that model from Thingiverse and start editing it in Fusion 360? Half of the responses basically said, you should just rebuild that from scratch. Don't even bother trying anything else because it's either impossible or it's a garbage result. And I'm here to tell you that Fusion 360 has cracked the case or unlocked the capability, and you could do a whole lot more than you ever thought possible right here in Fusion 360. So let's get back to that agenda, and now we'll get into the really good stuff. I'm glad you bared with me for a few minutes while we covered the basics. Now that you understand the basics, let's go into what you can actually do in Fusion 360 with mesh files today. All right, we're going to start by talking about how you can import mesh files and the different file types you could import. We're going to talk about repairing problematic mesh files and how easy and quick it is to do that. We're going to talk a little bit about face groups and what they are and why they're actually useful and important. We're going to talk about editing the mesh both parametrically and non-parametrically. And when I say non-parametrically, we often use the term direct editing. That'll make more sense in a few minutes. And then lastly, we have 3 different ways I'm going to show you how you can work with those meshes, how you can convert the mesh into a solid in 2 different ways, both what we call the faceted approach and the prismatic approach. And then I'm also going to show you how you can take solid geometry and turn it into meshes to be able to edit very complex meshes. So these are some detailed workflows. We're going to go through them one by one, and you're going to be able to see how you can actually use them to your advantage. So with that, it is time for our live demo. Here I am back in Fusion 360, and we're going to talk a little bit about how to import meshes. This is a good example of a mesh. This one actually comes in with a color map. And I don't know if you know this, if you don't, you will now, but OBJ files and 3MF files support color and texture. And Fusion 360 now supports the color or texture that's in those files. So when you import a 3MF or OBJ file that already contains color information, you might see a mesh that looks something like this one. If you don't see the color, either the mesh itself doesn't have the color information, or you do not have your display settings turned on to be able to actually see it, but you can actually bring in color information just like this. But let's start off from scratch. I'm going to go and open a new design here. I'm going to go to my mesh tab right here at the top, and under create, I can choose insert mesh. We're going to go and grab a mesh file from my computer, and we're actually going to start with an STL. STL files and OBJ files are unitless. So if you weren't aware of that, when you save a cube that's 1 inch by 1 inch, that STL file just registers as 1 by 1. When you import the STL file, you'll get a dialog box here on the right that asks you what the units are. If you choose millimeter and the document was really created in inches, you are going to get the document showing up in the wrong size. But if you match the unit type here with the original document, this will come in the right size every single time. So I can choose from a variety of different options here. Millimeter is correct, and I'll go and hit OK. Again, this is going to apply for your STL and your OBJ files in particular because they are unitless. If, however, you open a new design, you go to Mesh and Insert Mesh, and you choose a 3MF file, and that's my preferred file type for this exact reason. I can go and choose one. I'm going to go and bring one in that has some import errors. But when I bring this one in, you'll notice it doesn't ask me for the units because the 3MF file already has units built in. And I could just go and hit OK and look at that same mesh. Now, this particular mesh file does have some issues. I can actually kind of see them already. I have some holes in this particular file that are going to be problematic if I want to 3D print this. And I do a lot of 3D printing, as you could tell from the printer behind me. It is a MakerBot Method X Carbon, by the way, and is a phenomenal machine. But I need to fix this mesh in order to actually go and 3D print it. So I have a couple of different ways that I could do that. I could go under this bodies folder here, and I could see a yellow warning telling me that this mesh is not closed, it's not oriented, and it does not have a positive volume. Those are bad things to not have. I can actually click on the yellow triangle or yellow warning, and it automatically brings up the repair tool. If you didn't happen to want to do it that way, you can also just go to the mesh workspace, and under prepare, you'll see repair as an option. It's also right here at the top as well. And I could go and choose that mesh, and I have a variety of different ways that I could go and fix this mesh. Close holes, stitch and remove, wrap and rebuild. These are the high level different repairs you could go and make. I'll also point out that when you hover over them, it'll tell you a little bit more about how it's actually going to repair that mesh and the relative speed between each of the options that it will take to actually do the math to repair it. You can also go to the rebuild option, and I'll tell you that rebuild has its own separate options. There are 4 of them. So all in all, there are 7 different options for how you want to rebuild or repair your mesh. You can also hit this checkbox here, this preview button, which will show you what it will look like when it finishes repairing that mesh. And we do also have an optional analyze defects thing or feature that you can turn on here. This one you have to turn on in your preferences, but once you do, it'll actually analyze for you in a lot more detail what was wrong with the mesh. And if I uncheck the preview, this is showing me what's wrong with the mesh before it actually repairs it. And if I hit the checkbox, this is going to tell me what's wrong, if anything, once it repairs that mesh. So this is a great tool to be able to go and fix your meshes. And I do recommend you do that early on rather than later, because a problem in that mesh early on is going to plague you for the entire time you're working with that mesh. So these are just some great quick and easy repair tools to be able to fix your mesh and then be able to do your job. Now let's talk a little bit about face groups. So face groups are an interesting thing. Face groups are a way to be able to split up your mesh into sizable chunks based on the shape or the geometry that you see on the screen. Right now, this particular mesh is a single face group. If I right click on the body and I go to properties, under mesh here, you're going to see that it can tell me all sorts of different things about the mesh. How many facets I have, how many vertices I have, how many face groups I have, in this case 1, how many shells I have. Shell is basically like a sub body, so I could see one body on my screen but still see multiple objects. The shells are basically the objects. And then I can also see if there is texture and if there is color. So I said earlier that we support those things. This is how you're going to actually be able to see them. But right now there's only 1 face group, and that's not exactly ideal. So how do we go and create face groups? Well, you go to Prepare, Generate Face Groups, and choose the object you want to analyze and just hit the OK button. What it's going to go and do in the background is analyze the geometry to figure out which of these triangles or quads should be grouped together based on the geometry itself. Right now, I'm not actually seeing them, so let's go and turn on our mesh display and turn on our face groups. And now you could see the groupings as it created it so far. So this green here is this flat top. That actually did a great job splitting up relative to everything else. This orange did the same. This area, not ideal. I mean, in some respects, I agree that it should be grouped together, but it didn't really get to the detail level. It didn't split this up based on the actual fillets, and I probably want to split this up even further. And I could do that at any time I want. So just because I've already ran this generate face groups, I could always run it again. And I could run it again on a specific face group if I would like. So now I'll go and grab this specific face group, and I can even change the way that it's generating this face group. So right now I had, well, just a moment ago, I used the fast method. Now I could go and use the more accurate method, and it's going to go and use that more accurate method just on the face group I selected a moment ago. And that's really the key here, is when I went to go and use this tool, I got to select one face group instead of having to run this on the entire object or the entire mesh body. And that's important to note, because when you bring in a mesh into most engineering programs, you're really treating that mesh as a single object the entire time. But with face groups, it allows you to get into a little bit more detail in grouping things together based on what you might need to work with. So in this case, it figured out that this is its own arc. This is another one. It's actually almost a full cylinder. I have another arc over here, and so on. And I could generate as many face groups as I need to be able to create all of the detail that I want in this model. And that's going to be important, because when you go to edit the mesh, you go to modify, all of these tools you're going to see here. Everything from shell, combine, smooth, plane cut, all of these tools are really going to be working at the body level or the face group level. So you can, for example, plane cut at a specific plane, and it's going to be acting on a certain body, or you can use the shell command, which is like hollowing out the part, great for SLA printing, by the way, and you can shell the entire body, but at this point, not yet face groups, right? But the point here is that all of these tools are going to be based on the face group or the body. So if you do want to get to the face group level, you have to generate those face groups first. Now, many of you might ask, what's all this business about bodies and face groups when I'm used to editing meshes on the triangle level or the polygon level? Well, in Fusion 360, you can do that too. If you right-click on your body, you're going to see here Edit Feature. Edit Feature is going to create a mesh base feature that you can edit directly. And a base feature is a very interesting thing in Fusion 360. So let's talk a little bit about parametric modeling. Many of you, 41% of you, came from SolidWorks. A large percentage, I don't remember the exact number, but a large percentage of you came from Creo, NX, CATIA. All of these softwares are parametric. They're history or recipe based. And when you're working with meshes, or at least in the past, the recipe didn't exactly exist. When you were editing those meshes, you were editing them directly, or without the history, or non-parametrically, as I would say. Fusion 360 allows you to edit meshes parametrically or non-parametrically. You get to choose. If you would like to edit that mesh parametrically, you're going to be making your modifications based on the bodies or the face groups. And if you'd like to work on the pixel level, so to speak, the 3D pixel or the triangle or the quad, that's fine too, but that technique is definitely going to be non-parametric. It is going to be using the direct editing capability in Fusion. So let's actually go and do that. I'm going to go and choose Edit Feature. Now you can see the top Direct Mesh Editing. And if I use, actually, let's turn on my mesh palette here so you can see this nicely. And now I can go in and select individual meshes. Actually, I think I might have misselected here. Let me try that one more time. There we go. So when you're selecting these individual pixels, you'll see that we have a selection palette. This is going to make it a lot easier for you to actually select everything. You could select one triangle or lots. It's really your choice. And once you do that, you can then act on it and make changes to it. So erase and fill, for example, is a feature that you will not see in the parametric side of things, but you will very much see in the direct mesh editing side of things like we're in right now. But the key here is that depending on what you're trying to do, you can edit the model directly and work on the 3D pixel level, or you can edit the model on a face group or body level as well, and that will all be parametric. And that to me really opens the doors on an incredible world of possibilities of how you're actually going to go and edit the mesh. That really does allow you to be able to make fast changes. And the best part about it is that when you are making those changes to the parametric model, you still have parametric feature history. So let's go and grab an example. Let's actually go and open up one that I haven't opened yet. This one right here, I think, is a good example. So this one here is going to show you one of the workflows that I was going to show you in just a few minutes. Actually, I still will show you in a few minutes, but let's talk about it. I have a mesh base feature that imported the mesh. I have a sketch of all of these positions of these holes. I have an extrude feature, and then I have a thread feature, converting that thread into a mesh and then combine it. This is parametric modeling at its finest. And if it turns out that I want to change the size of the thread, I can always go back and edit the feature. And instead of this being an M4 by 0.7, maybe I'm going to make that an M4.5 by 0.75. I just go back and I change that feature, and it's going to go and update the entire model. This is going to work both with the solid modeling features that you're used to and also with the mesh features themselves. And that to me is absolutely incredible. All right, so let's get back on track. I told you that we were going to show you 3 different ways to convert meshes into usable geometry, right? So 2 are going to show you how to convert the mesh into a solid, and 1 is going to be the exact opposite. Let's start with the very first. So I have a mesh file. All right, maybe this one right here. And I want to go and convert this into a solid so I can cut a hole in it maybe. I'm going to go into my mesh tools, convert mesh, and I'm going to change this to a faceted option, select the body and hit OK. Now this is going to work for as many polygons as you'd like. In the past, this was limited to 50,000 polygons, but we used to give you a pretty harsh warning after 10,000, and some people thought that meant that the limit was 10,000. In reality, the limit at the time was 50,000, but the limit now, whatever you would like. I will tell you this comes with performance costs, because if your hardware can't keep up, then you will have slow performance, but theoretically you can have as large of a mesh as you would like and still convert to a solid. You can see under the bodies folder here, it says mesh body 1 because that's what it was called when I imported it, but this gray silver icon here is really telling me that this is a solid body. If I wanted to go and cut holes in this or chop things, I can go and do that no problem. I can also clean up this mesh as well, or really it's not a mesh, clean up this solid, right? Because right now I have a lot of polygons. If I select a flat face like this one and hit the delete key, it will do its best to try to merge all of the flat faces together that are within a tolerance. I could do the same thing on this top surface right here. That should clean that up. I'll do that same thing over here as well. I might also do the same on this very top level, and maybe even on the bottom as well. But this will not work on cylindrical faces. This will not work on fillets. This will not work on chamfers. This is really limited to flat faces. And when you do have a flat face, it works magically, but this is still going to be limited to those flat faces. Once you have a solid like this, whether you choose to clean it up or not, you can still make all of the changes you'd like. So for example, if I wanted to make this hole bigger, I could go and create a quick sketch. I'm going to go and draw a quick circle here. I'm going to go and put it on 3 points. So I line it up nice and perfectly. I could then go and take this and add a new circle with the same center. And of course, choose my new diameter. Let's go and do that. And maybe we're going to go with 23.5. And we could go and extrude that all the way through my solid body. Just like that, I now have a pretty significant change to a mesh file, whether that mesh file came from Thingiverse or from your engineering department or your reverse engineering department. Point simply being, if you would like to convert your mesh into a solid and then edit it, this is a great way to do that. And cleaning it up on the flat faces, absolutely perfect to do in Fusion 360. But what if you would like to be able to edit it even more easily? Well, you could do that too. Let's go and delete our parametric history here because we're not going to need that right now. And actually, let's delete the conversion. Right before the conversion, you'll notice that I already have this generate face groups command. You do not need to generate face groups to convert to a solid using the faceted option that I showed you. But if you would like to use the other option, the magical button that is prismatic, that one you are going to need to generate face groups first. So this model already has those face groups created and everything is looking really good. I have my filleted areas or my arcs. I have my flat bottoms. I have everything looking exactly how I would expect. So I'm very happy with this. Now we'll go and do a conversion. And instead of choosing the faceted option, I'm going to go and use the prismatic option. I'll go and select my body and hit the OK button. And I watch as in just a couple of seconds, Fusion 360 automatically converts each of those face groups to an individual face of a solid body. Just like before, this is still a solid body, but look how much cleaner this is. Not only are the flats flat, but I also have cylinders for the cylindrical faces. I also have essentially cylindrical faces for my fillets as well. I have proper chamfers where the chamfers should be and a whole lot more. This is a great model. This is a lot easier for me to work with, great performance while I'm working with it, and I can make changes to this model very quickly and very easily. So if I wanted to, for example, extend the bottom of this blower, I could simply select it and use the press pull command or the, in this case, offset face command So simply drag this and add 10 millimeters. If I want to add a fillet, I could go and add a fillet to this as well. That's a little bit big. Let's go with 2.5 millimeters and hit OK. If I want to change the diameter, I can actually go and select the outside face or the diameter here and drag this and add another 2 millimeters in this case. This is all possible because Fusion 360 has a direct editing or direct modeling kernel built right into Fusion 360, and also Fusion 360 has the ability to convert that mesh into a nice, clean solid. And you combine those two things together, and now I have STL file editing made easy. So you can take models from Thingiverse or from your engineering department or your reverse engineering department and be able to make changes to them very quickly and easily. This capability that you see here is going to work much better on geometric shapes. Remember that the method itself is called prismatic, and it's called prismatic for a reason. It works much better on prismatic shapes, less so on like scan data, for example. It still can work, but it's going to work much better on prismatic or geometric shapes. And I will note that while Fusion 360 does have a free version, this is only going to be available in the commercial license. So the free version is not going to have this magical convert option. If you're using Fusion 360 for any of your hobbies, it is still worth the $495 to be able to buy Fusion to be able to do this. At least in my personal opinion, I leave that up to you. But just know that if you're considering Fusion 360 for your business, this is an absolute game changer in what it can actually do. And I question how much of this you're able to actually do today in whatever software you're currently using. Because like I said, I've never seen these capabilities anywhere else. These are astronomical. There is one other method that I have not covered yet that I have the feeling you would like to see. What happens when your mesh is actually so complex that you don't want to convert it to a solid? Remember I said earlier that if you convert to a solid using the faceted option, you're going to have a big performance hit, especially if that mesh is very complex, right? So if you have a mesh that is overly complex, you might not want to actually convert it to a solid. And the reality is you don't need to. So let's actually go and show you that example that we looked at earlier, but let's show it to you again. So I started in this particular case with a mesh file. Looks just like everything that we've been looking at so far. Then I made a sketch, and that sketch, let's actually hide the body for a second. You can see all of these circles. Whoa, show it, there it is. All of those circles represent the whole locations on the top of this gearbox cover. And I need to put threads there. And the original mesh file, no threads. I definitely need to put threads in this that are going to be 3D printed. So I have a sketch for all of these locations. And then what I did was using standard solid modeling, not mesh editing, not mesh modeling, using standard solid modeling, I created a cylinder right here where I want those threads to be. And if I hide the mesh itself, you can see that cylinder is actually going down into the mesh, right? Next thing I did was I used my solid modeling thread feature. Now I have my modeled threads. And if you go into this feature, we've already been in here once, but if you go in here, there's a checkbox for modeled. Otherwise, it'll be a cosmetic thread. So definitely hit that modeled button. And once you do, you pick your thread size, and here you have your solid body with your threads on it. But we wanted to make the threads in the mesh. And most people assume, we all know what happens when you assume, that you have to convert the mesh to a solid to put threads on it. Instead, I'm going to challenge your way of thinking about this. And instead, we're going to make those threads as a solid, and we're going to convert it into a mesh. So under the Mesh tab, I also have the ability to tessellate a solid body. I can tessellate this particular solid body with the threads. And now I have a mesh with all of the thread features on it. I still have my original mesh taking up the same space. And I can use my modify combine right here to be able to act on the two. Remember that the combine feature is parametric and is going to use bodies or face groups, but in this particular case, combine is actually limited to bodies. That's okay. The target is going to be the gearbox housing, the tool is going to be the solid body that was converted into a mesh. Let's go and select that right over here. We don't actually want to join them together right now, but actually you can see that if I did want to create a boss that was threaded, I would just keep this as join. But in this case, we actually want it to be a recess that is threaded. So I'll change this to cut and hit the OK button. And in just a matter of seconds, you're going to have a thread within this particular part. And that to me is an absolutely incredible workflow, because instead of converting the mesh into a solid to be able to put on that threaded feature, instead I actually used my solid modeling tools and combined it with my mesh editing tools to be able to add my threaded feature. And this can get as complex as you would like, right? Fusion 360 is all about versatility in the way that you model. And you have solid modeling, surface modeling, subdivisional modeling, you have sheet metal modeling, generative design, and now you can combine all of that also with the mesh editing capabilities in Fusion 360 as well. And when you combine that together, you end up with a platform to be able to design mechanical enclosures, electronics, and everything in between, fully analyze those designs, and then of course manufacture them all in one solution. So to me, that's an absolutely incredible proposition. Let's go and take a look at our agenda once more. We did our live demo, and this is what our plan was, right? We talked a little bit about me. That was the boring part. We talked a little bit about Autodesk, about mesh bodies, and gave you a fundamental or foundation of what mesh bodies really are and why they're difficult to work with. Then we jumped into the really good stuff of what you can actually do with mesh files in Fusion 360, how you can edit them, how you can interact with them, how you can be able to edit them parametrically or through direct editing, and all the different ways that you can convert them back and forth from meshes to solids or solids to meshes. And don't forget that the hybrid of the two is the real game changer here. And that's what I think allows you to be able to open up all the doors of what you might actually want to work on. So that's a summary of what we covered today. Now I think we're going to leave time for Q&A. So with that, I'm going to hand it back over to Maria to see what questions you might have for me today.
Thanks so much, Jason. Here's our first question. Can you convert organic shapes? And if so, is this capability available in the educational version?
Great question. So you can convert organic shapes. However, right now, and I say this now with emphasis, your method to convert your mesh to solid is limited to either the faceted approach or the prismatic approach. Remember that the prismatic approach works better for the prismatic shapes and relies on face groups. The face groups themselves are going to be harder to generate correctly for the organic shapes. So for organic shapes, I typically use the faceted approach. But the faceted approach also comes with some limitations as well. Remember that it's going to create a facet or a face for every single polygon that was in your mesh file. So if you're working with something small that's 10,000 polygons, maybe not a big deal. If, however, it's 200,000, 500,000, a million polygons, that could be problematic. So in that case, I recommend maybe not converting from mesh to solid. I would recommend that last option that I showed, where you take your engineering features and you add it to your mesh file. I will also tell you, and I can't give you all the details, but I will tell you that there are plans for a third option that might be even better suited to organic shapes like you described. It is not available yet, but I'm looking forward to it being available in the near future.
Awesome, thank you. How do you control the resolution of the mesh?
Great question. So when you're converting from a solid to a mesh, you're going to have the option to be able to choose the resolution. There's actually a whole lot of options when you're tessellating a solid body to be able to choose the resolution. Once you have a mesh, if you would like to re-tessellate the mesh or remesh the mesh, you can do that as well. And in those features, there are options to be able to do so. When you're converting from a mesh to a solid, again, those features have certain limitations based on the way that they work. That faceted approach, there's no real resolution setting because you're going to get a facet for every single polygon. And then on the prismatic approach, it's going to be as detailed, or like the resolution level will be as detailed as the number of face groups that you have. So keep in mind, I think your question's more related to going from solid to a mesh, and we have plenty of options in those features to be able to choose.
Great, thank you. Next question. I would like this tool to convert an STL file that comes from a laser scanner, which is highly irregular. Can I still use face groups to get something useful, convert to solid?
You can. I will tell you, just to repeat, that for things like 3D scan parts or parts with irregular shapes with imperfections in it, in my opinion, the face group creation is going to be problematic. You can create face groups and you can get to a certain point that you might be happy with it, but the real best way to convert those files is simply to use the faceted approach, at least today. So when I'm doing my conversion of scan data into a parametric model or even a dumb solid, I usually start with the faceted approach and then I clean up my model. I do have a couple of other techniques I use that are kind of a hybrid of the two, but I don't recommend just using the face groups option because I think you're going to struggle to get exactly what you're really after.
Awesome, thank you. Can you give some examples of a real-world workflows on how or when you would use mesh versus solid models?
Oh, I can give you the best one. All right, so I'm going to change my screen again. Let's go back to Fusion 360 for a second here. I'm going to open up a new model for you. All right, so this one is one that I think really shows a hybrid approach. I said earlier that you can solid model, surface model, sheet metal model, use generative design, use subdivisional modeling, and use your mesh editing. And you probably thought to yourself, how on earth could you use all of those together? This example, I think, is a great way to see all of those together in one place. So this particular example is a 1963 Jaguar S-Type. And in this particular case, we're going to focus on the hood ornament. If you haven't seen it before, this is called the Leaping Jaguar. And these are very common in the older vehicles. And some of them are very rare, and some of them are simply impossible to find. Right? So if you look on eBay, you might be able to find a new old stock one of these, but sometimes really the only way to be able to create one is to start from scratch or to start from a 3D scan. And this is a perfect example of that. So let's actually go back in our timeline here just a little bit. If we go back in our timeline, right now you can see the Leaping Jaguar, which I imported, and it's in the right location. I've already positioned this relative to where it should be using the following image. Right, so here I have an image of the Leaping Jaguar in place. I have two images actually, as you could tell here. And here you could see the Leaping Jaguar in position. But if you recall from that canvas that I saw, never showed you, the base of this Leaping Jaguar is very organic. That's the kind of thing that would be best suited for modeling using subdivisional modeling. So what I created here in our timeline is a base using subdivisional modeling. And if I go in and I edit this, let's actually hide the Leaping Jaguar for just a second here. Oh, wrong one. There it is. Here you could see the subdivisional model that I created with symmetry for that particular shape. Keep in mind though that right now it's not mated against the hood correctly. Right now it's interfering with that hood. But that's okay at this point. I create my shape and it converts it into a surface. But I, of course, want a solid. So I use surface modeling to take the bottom and patch it, then stitch that together, which converts this into a solid. But at this point in time, it still interferes with the hood itself. But I can I can convert the hood itself into a solid body. So now you could see a solid body for the hood and a solid body for the base. And I could do a Boolean combine as solids to get rid of the hood from that base. Now I have a perfect base that's going to fit on that hood, but I have no mounting information. I have no threaded holes. I have no mounting like positional pins. Well, we can go and create those as well. We can create a sketch. Let's actually go and show them. So this is where my holes are going to be, and this is very precise, right? I can use my engineering sketch with my position of my holes and everything. So this is everything looking really good. Pardon the dark colors, it's a little hard to see right now. Then I can go and create my solid geometry. Let's actually show that a little bit better. Create my threads, combine that with my base. So now I have a base with threaded holes that are in the exact right location, but this is a solid body. My leaping jaguar is a mesh body. Well, I can also tessellate that solid body into a mesh and then combine it back with the original mesh. So now I actually have, sorry, there it is. Now I have a mesh body that shows everything combined. I started with just a mesh by itself. I then used the form tool to create an organic shape. I used surfacing to close that shape and turn it into a solid. I used my conversion of mesh to solid to be able to cut out the hood so I have a perfect fit. I used my sketch and engineering constraints to be able to create geometry in the base that's absolutely exact. And then I converted or tessellated that solid into a mesh and combined it with the existing mesh. If that's not a complicated workflow, I don't know what is. But I'll tell you right now that that hybrid of all of those different workflows would allow you to make a hood ornament where I would think that it would be very difficult, if not impossible, via any other means. So I know that was a very long answer to that question, but I think it was worth it because it really just shows the power of what you could do with hybrid modeling.
Yes, absolutely. Thanks for that additional demo. Next question. Is Fusion 360 a good fit for designing dental aligners using 3D scans?
Ooh, great question. I would say the short answer is yes, but the reality is there's a lot of detail in what you might be using it for in particular. Is it that you're trying to take those dental scans and convert it into the aligner itself? Are you trying to use the scan to actually machine, for example, a mold that you're going to thermoform the aligner around it? There are a lot of different possibilities of what you could be using it for. And so let me throw out an idea for you. What we offer at Autodesk is the following. If you or your business is considering Fusion 360, sorry, let me rephrase that because that was a nuance that's important. If you are considering Fusion 360 for your business, not for your hobby, but if you're considering Fusion for your business, we offer a free one-on-one consultation to learn a little bit more about your business, what you're currently using, what your current workflows are, and what your needs are that you're trying to accomplish. What are your goals and your aspirations? Based on that, we can actually tell you a much more detailed answer of whether Fusion 360 would be a good fit for you, why, and we can actually demonstrate that workflow itself. So keep in mind that we offer this. If you're considering Fusion for your business, feel free to reach out to us. Actually, I have a slide for that. There it is. This is contact information to reach out directly to Autodesk. If you're in North America, if you're in Europe, in Japan, India, Australia, or New Zealand, we have contact information both via the phone as well as email. Feel free to reach out to us. We would be happy to set up a time to meet with you, to learn about your business and see if Fusion 360 would be a good fit for you. And if so, to actually demonstrate the workflow for you directly.
Awesome. Thank you. Well, that concludes our webinar for today. Thank you, Jason, for your great presentation, and thank you, attendees, for joining us. We hope to see you all again for our future webinars. Bye for now.
Thank you.